So this is the last essential topic of the. So, an example as usual. We're going to consider a thin iron rod. We'll suppose that it's insulated at the sides. This is going to be a temperature problem. The rod is 2 meters long. It's 100 degrees throughout at time 0. And we're measuring time in seconds, length in meters, and temperature in degrees Celsius. So you can already see there's a lot going on here just by looking at the units. We have length, time, temperature. At this time, we hold 2 blocks of ice to either end of the rod. And we're going to suppose the blocks of ice are 0 degrees Celsius. And I ask, when will the center of the rod reach 50 degrees Celsius due to this cooling from the blocks of ice? The first thing we need to do to solve this problem, there's going to be a lot. The first thing we need to do first is write a model for the problem. So first of all, observe that the temperature of the rod at any position and any time can be thought of as a function of those two variables, position and time. Thus, temperature depends on where you are on the rod and what time it is. So you can imagine here's the rod, and the 2 blocks of ice are here and here, and I've drawn this brown insulation to indicate that no heat is escaping or entering the rod at the sides, only the end points where the ice is. And it's a little bit small, but we're going to consider the left end point of the rod to be at position 0 and the right end point of the rod to be at position 2. And what we will do is we're going to analyze a thin segment of rod from the position x, where x is some arbitrary position between 0 and 2, and x plus delta x. So we have a very thin slice of rod, and we're going to figure out what happens to that thin slice in terms of temperature. So we have to zoom in, and if we look closely at it, and if we consider a short time interval from t to t plus delta t, so imagine allowing the clock to run for a very short amount of time. Let's imagine 1/100th of a second passes. And the question I'm asking is, how much heat enters or leaves this little tiny segment of rod? So what we're going to do, I've updated the picture now, is we have we're considering this little slice right here, and in order to do that, what we're going to do is we're going to consider its 2 neighboring slices, here and here. And because neighboring slices will interact with each other, the thinking is that if one slice is hotter than another, it's going to transfer heat from itself to the cooler slice. So if we consider the temperature of the rod at this very special slice here between x and x plus delta x, if we call the temperature there T, let's call the temperature of its neighbors TL and TR for left and right. Now the heat transfer from the left slice to the center slice will be proportional to the difference between the 2 temperatures. So for example, if the left slice is hotter than the center slice, then heat will transfer from the left to the center slice. On the other hand, if the left slice is colder than the center slice, then there will be a negative transfer of heat, meaning heat will exit from the center slice to the left slice. So we conclude that the temperature that goes from left to center is proportional to TL minus T times the amount of time that we allow this to occur. The more time that passes in this short time interval, the more heat will transfer. So, if we also look at the right-hand slice, the heat transfer from center to right will be given by this, by similar reasoning. Then we're also going to use this fact, this empirical fact, that the change in energy of our center slice will be proportional to the amount of heat that it gains from the left slice minus the amount of heat that it loses to the right slice. And energy is proportional to mass times temperature. Energy is proportional to mass times temperature. So change in energy is proportional to mass times change in temperature. Now, if we put these together, change in energy is mass times a constant times a change in temperature, where the constant is the proportionality constant here. Then we also know that mass is equal to density times the length of our slice. So we have this. There's actually a mistake. There should also be a C here. And moving on, the change in energy is also equal to the amount of energy gained from the left minus the amount of energy lost to the right. And these two quantities are proportional to these differences times delta t. So I put them together, and here they are. But then what is TL? TL is just the temperature at position x minus delta x at time t. T is the temperature at x at time t. TR is the temperature at x plus delta x at time t. So these are true for this. On the right-hand side, we have rho c delta x delta t. Well, the change in temperature is just the temperature in the future at t plus delta t minus the temperature at the present. That's the change in temperature. So we have this. And then if you so now we're using linear approximation. This expression here is approximately equal to the partial derivative of t with respect to x times delta x, and this is the partial derivative of t with respect to x at x comma t, all times delta x. If you want linear approximation in your favorite calculus textbook, you can do that and try to make sense of this, but I do not believe I am going to explain this. Linear approximation. Approximations are really good. They actually get better and better as delta t and delta x approach 0. Moving on the right-hand side, I actually did not change anything, so it's just that. And finally, using linear approximation again, this entire quantity is actually the partial derivative with respect to x twice of the temperature function at x minus delta x comma t times k delta t delta x. And on the right hand, so we have this equation. We got to using a bunch of linear approximation. And if we bring the k over and let delta x approach 0, it becomes this extremely famous equation, the heat equation, where, so we've rewritten it here, and we know that the rod started at 100 degrees Celsius at time 0, so we know that the temperature at any position x at time 0 was 100. But we also know that because we placed ice cubes at both ends of the rod, and we're going to assume that they don't melt, so we're assuming they're large enough that they remain as ice, then the ice is going to keep the ends of the rod at 0 degrees Celsius, which says that the temperature at position 0 will be 0 for any time t, and the temperature at position 2 will also be 0 at any time t. So we have our partial differential equation, and we have these here. These are the equivalent of initial values. This is like an initial value problem, but it's a bit more general. It's a bit harder. This is what we have with partial differential equations. First of all, notice that we have an unknown function, capital T, for temperature, of 2 or more independent variables. That's the hallmark of a partial differential equation. It depends on 2 variables, x and t, and instead of just initial values like f of 0 equals 1, we have boundary values where we have basically infinitely many initial values. We know that the rod is 100 degrees for any value of x at time 0, and the rod is 0 at the endpoints for any value of t. So we have you can think of it like we have infinitely many initial values rather than just 1 or 2 or 3, and these are called boundary values for partial differential equations. So in summary, so how do we do it? Well, here's an idea. The first idea, which is mostly attributed to the mathematician Fourier, is to attempt to find solutions of the form f of x times g of t. So not all, for example, x plus t is not of this form. Clearly, by guessing that our solution has this form, f of x times g of t for some functions f and g, we're not considering all possible solutions, so we are severely restricting ourselves. Now let's see what kind of solutions we can find. So we substitute this guess into our differential equation, and notice that the partial derivative of this function t, which is f of x times g of t, with respect to x, well, here we have a function of x and here we have a function of t. So to differentiate twice with respect to x just means you end up taking 2 derivatives of f, but the function g of t isn't affected since there are no x's here. This is just a function of time. Similarly, the partial derivative of this guess with respect to time is just going to be f of x times the derivative of our function of time. So when we plug this in here and this in here, we get this equation in the 2 unknown functions f of x and g of t. Now, this might seem like a pretty intractable problem, but if you rearrange it, well, okay, this is interesting, but the mathematician Fourier, who lived in the 18th and 19th centuries, he was a big fan of Napoleon. He was a French guy, and he and Napoleon really liked each other. And he even ended up managing some kind of province. He was given given an entire province after Napoleon's conquest of much of the world. Anyway, so he got along with Napoleon, but he was a really smart guy too, and he figured out this. He figured out how to solve these equations. He noticed that, well, really, Fourier developed this entire technique. He noticed that the left-hand side is a function of x, and the right-hand side is a function of time. But if you have a function of x here, and you have a function of time here, and they have to be equal for all x values and all time values, then it must be the case that they're both constant. I will just leave you to think about that observation for a moment. You should definitely convince yourself that this is true. There's no way that this could be changing, because if you were to change x and get a different number here, but leave t the same, then you'd have two different numbers here equal to the same number here, but that would be impossible. So they must be equal, but I mean, they must both be constant equal. They cannot change for any values of x and t. So if they're both constant, then they're both equal to the same constant, which we're going to call negative lambda. We don't know what that constant is, but they are both definitely constant. So we have two equations. This is equal to lambda, and this is equal, to negative lambda. So if you multiply through by the denominators in those two equations separately, you get f prime prime of x equals negative lambda f of x, and the other equation, g prime of t, equals negative lambda alpha g of t. All right, so we have two equations. Each one of them is an ordinary differential equation, just in terms of x or just in terms of t, which is pretty wonderful, because we know how to solve those. And if you let y equal f of x, then you get y of 0 equals y of 2 equals 0, and you get an ordinary differential equation, y as a function of x. So we know how to solve these. We just solve the characteristic equation. But unfortunately, we don't know what lambda is. Lambda could be negative for all we know. It could be 0, it could be positive, and we actually should consider all three of those cases separately. If lambda is negative, then we can write lambda as negative some positive number squared. And if you do that, then the characteristic equation just becomes r squared minus eta squared equals 0. Therefore, r equals plus or minus eta. And therefore, our function y as a function of x is c1 e to the eta x plus c2 e to the negative eta x. On the other hand, if lambda equals 0, then our function y of x is, well, this is a repeated root situation. We have y prime prime equals 0. The characteristic equation squared equals 0. That's a double root, r equals, and it gives us the solution c1 plus c2x. On the other hand, if lambda is greater than 0, then lambda can be written as eta squared for some positive number eta. So r squared plus eta squared equals 0, r equals plus or minus eta I, and the solution is c1 cosine eta x plus c2 sine eta x. But now we should consider the initial conditions, y of 0 equals y of 2 equals 0. the initial conditions yield, let's look at this first. If you plug in 0 for x, it's starting to storm outside. If we plug in 0 for x, then you just get, well, this isn't entirely accurate, at least not yet. Well, you'd actually get C1 plus C2 equals 0. So let me write that. You'll see in just a moment. I'm not entirely wrong here. If you plug in the other initial condition, y of 2 equals 0, then you get, oh my goodness, I'm sorry for these typos, but if you plug in these, if you plug in the initial condition y of 2 equals 0, you just get e to the 2 eta c1. There's no eta here. For some reason, I took a derivative, and this should be a plus sign. So there are no etas. It's just e to the 2 eta plus c2 e to the negative 2 eta equals 0. So yeah, forgive the typos here, but we have c1 plus c2 is 0, and c1 e to the 2 eta plus c2 e to the minus 2 eta equals 0. This is actually a system of equations in two unknowns, c1 and c2, and you can check that it is a non-singular system. If you write out the matrix and take the determinant, it's going to be non-zero, which means this does not have a null space, and so the only solutions are c1 equals 0 and c2 equals 0. It has a trivial null space. And so the only values of C1 and C2 are trivial. So we actually don't get any interesting solutions from this column when lambda is less than 0. On the other hand, if lambda equals 0, then the first condition gives C1 equals 0. The second condition says that C1 plus 2C2 equals 0. But this is 0, so this has to be 0, so they're both 0. And once again, we have no non-trivial solutions. All we have is y equals 0. That's not very interesting. Finally, if from these applying these initial conditions, y of 0 equals y of 2 equals 0, for this solution, if lambda is greater than 0, we have C1 equals 0. But then we have C2 sine 2 eta equals 0. Now I ask you, does that mean that C2 is 0? It does not. Usually it would mean that C2 is 0, but it's also possible that sine 2 eta is 0. If sine 2 eta is 0, then we're allowed to take non-zero values of C2. So, if 2 eta is a multiple of pi, giving 0 here, then we have C2 can be any number we want. So we conclude that we have a non-trivial solution if we just let C2 equal 1 and we let eta be any multiple of pi over 2. I just divided this equation by 2. We conclude that that f of x is a solution if it's of the form n pi over 2x. And if you don't believe me, you can check two things. You can check that it satisfies this equation. Well, of course it does, because it satisfied the characteristic equation. But you can check that nonetheless. You can check that this equation is satisfied, and it also satisfies the initial conditions. Seriously, you should really check it. So this works, provided we take, because recall that lambda is eta squared, and eta is n pi over 2. So therefore lambda is n pi over 2 all squared, which is n squared pi squared over 4. Lambda sub n. Values of lambda that work. In fact, there's infinitely many of them, as we'll discuss in a moment. And now we go over to our other equation that g of t had to satisfy from our separation of variables. And g of t satisfies this. This is actually not too bad. This is a separable equation. When you let y equal g of t, you can separate variables in the ODE's sense of separating variables. And so we have dy over y equals this. Integrate both sides, and solve for y. So our goal from the beginning was, or our idea, was to try to find solutions of the form f of x times g of t. We figured out that there were lots of ways to do that. F of x could be any function of this form, and g of t has to look like this, if f of x looks like this. And since we found so many solutions, I subscripted them with an n. So this is every possible solution that satisfies these boundary values here. So no, we did not find one solution. We found an infinite series of them. So for example, f1 of x is sine of pi over 2x, f5 of x is sine 5 pi over 2x. These all work. So why in the world would we be interested in finding infinitely many solutions? These are all solutions to this partial differential equation. You can check that too, by the way. So what? We even know that they satisfy this boundary condition. Well, that's great. Well, that's a problem. We chose them so they satisfy the differential equation, so they satisfy these initial values, but they do not satisfy this initial value. Here's the idea. While these solutions do not individually satisfy this initial value, if we add them together as a linear combination, an infinite linear combination, then they will not only satisfy the differential equation, but perhaps if we choose the correct linear combination, it will also satisfy this initial value. So let's try that. Well, if we write out this series, we don't know what the coefficients are, so they're b1, b2, b3. We have a temperature function, and we're going to try to add all these individual solutions together with constants b1, b2, b3, and we hope that if we choose those constants correctly, then this initial condition will be satisfied. Well, how does that work? Well, first of all, let's take this whole sum and let's write it in summation notation. B sub n sine n pi over 2x e to the negative n squared pi squared alpha over 4t. What is B sub n? We want the boundary condition, t of x 0 equals 100. The bar started at 100 degrees Celsius. So therefore, if we plug in x for x and 0 for t, we should have 100 equals all of this. Well, e to the 0 is just 1, so 100 equals this series. because our bar has length 2. But this is a Fourier series. What we have here is a Fourier series. It is the Fourier series for a function of period 4, because n pi over 2 is the same as 2 pi n over 4. So L is 4 in what we have here. So here we have a sine series. We want it to add up to 100 for all x between 0 and 2, because that's the temperature of the bar. That's in order for our initial condition to be satisfied, this has to be true. But this sine series will add up to an odd 4-periodic function. That if you have a series just with sines, so if you don't have any cosine terms, then the function you end up with is automatically going to be odd. Recall that an odd function is symmetric with respect to the origin. So odd functions look like that. Even functions are symmetric about the y-axis, so they look like that. So this, if you don't have any cosine terms, then you automatically end up with an odd function. Oh, I should move this off. That's going to be 0. Anyway, we have a sine series, so it automatically adds up to an odd function. And its period is going to be 4, because L is 4 in this formula. Well, what's an odd function that is 100 between 0 and 2, and it's periodic of period 4? Well, it's the square wave. If it's going to be 100 from 0 to 2, but it's also going to be odd, then it has to be negative 100 from negative 2 to 0. And then if it's going to have period 4, then it has to keep repeating. So our hand was forced. This series, if it's going to be correct, if it's going to be 100 from 0 to 2, it's going to be a square wave for all values of x. Let me get these. All right. See what we have then. So let's define our square wave function. It's 100 from 0 to 2. It's negative 100 from 2 to 4. And it's 4-periodic. So I define a 4-periodic extension, perhaps in the lab. But what I defined here is a of this function here. And then the terms, b sub n, or b of n in Mathematica, are going to be what you have here. 2 over L, integral from 0 to L, f of x sine 2 pi nx over L, where L is the period of our function f of x. The b sub n have to be equal to this in order for this to work. I tried typing in b of n and it gave me this, but that's kind of silly because we know that cosine n pi is just plus or minus 1, and we know that cosine 2n pi is just 0. Or I'm sorry, what am I talking about? It's just 1. So what gives? Well, Mathematica doesn't know that n is an integer unless I specify that it's an integer. So I refined that same expression, noting that n is an integer, and it gives me this nicer simplified expression. That I will explain in the lab. That's that when I was entering my formula for b of n, I had to integrate with respect to capital X rather than lowercase x. Usually the variable of integration doesn't matter. In mathematics, it never matters. But what you're not allowed to have is the variable of integration appearing outside the integral. So there's some confusion when we use x's here and then we use x's as a variable of integration as well. I'll try to explain that in detail why we do this. But I found that I could avoid some difficulties if I simply use capital X as my variable of integration. And that does not hurt anything. So these b sub n, these Fourier coefficients, are the first one's 400 over pi, the next one's 0, the next one's 400 over 3 pi. You can just plug in n equals 1, n equals 2, n equals 3, and you get these numbers. So it's actually forming a nice little pattern. And if we define the kth partial sum, the sum from 1 to k of b sub n sine n pi over 2x e to the negative n squared pi squared alpha over 4t, which I did here, where I let alpha be my diffusivity constant that was given at the beginning of the problem, then we can plot this solution. The reason I define a partial sum, notice that this sum is from 1 to infinity. So why am I doing a partial sum from 1 to k? Well, we're actually going to be doing some computations with this, and computers, as great as they are, aren't usually able to handle adding up an infinite series all that easily. So what we do is we truncate the series and just take the series from 1 to k. And we're going to use some different values of k, as you'll see in just a second here. So this is the diffusivity constant of iron, 2.3 times 10 to the negative fifth meters squared per second. And if you plot T2 of x comma t, well, what's T2 of x comma t? That's the sum from 1 to 2 of this expression. So it's the first two terms of the series. So if we plot the first two terms of this series, we get this graph. Now let's make sense of it. You actually can't see the labels too well, so I'm going to write them in here. This is the x-axis. Going out this way is the time axis. And up here, vertically, is the temperature axis that says how hot the rod is at that position at that time. Now the rod started at a solid 100 degrees. So it should be a solid line here. This is actually not an accurate solution, so don't read into this too much. But you do see that the rod is cooling down as time goes in the positive direction. So at least it has that property. But if we add more terms, so if we do T3 of xt, you get this picture. And if we add more and more terms, T10, so when will the rod be safe to touch at the center? It started at 100 degrees Celsius. We were curious when it was going to reach 50 Celsius. So we take our partial sum with 90 terms, and we ask at the center, which is x equals 1, and for what time t will we get 50 degrees Celsius? And I used the find root function because the nsolve function was acting up for this problem. I used find root and made my initial guess 15,000 seconds based on the picture. The correct answer, it turns out, was 16,467.3 seconds.